In this lecture, we are going to discuss about the threshold voltage of the MOSFET. So, what actually makes up the VTO? This is very important. So, the different physical parameters contributing into the VT naught. Okay, so what are the different parameters, physical parameters? Number one, when you have a MOSFET, at that time there is a difference between a metal and a semiconductor work function. So this is the first physical parameters basically which is there in the MOSFET calculations. The second one is because you wanted to invert the channel region from P to N, so that also contribute into the MOSFET to change the surface potential. The third parameter is when you convert this into P to N, before that there is a depletion region. So because of that depletion region, this also contribute into the threshold voltage. Then the fourth component is the fixed charges that exist in the oxides. So sum of all these voltage components basically contribute into the threshold voltage. So let's understand one by one each component. Because of work function difference between metal and semiconductor, it creates a built-in potential that the gate must overcome. So this is the first you can say term in the threshold voltage. The second term is to invert a p-type substrate into n-type. You require some gate voltage to convert that. Before inversion, the third component is before inversion, the gate field pushes holes away, so gate must apply additional voltage to create an electric field strong enough to balance the negative charges which are there in the depletion region. In real devices, there are charges trapped in the gate oxide. These charges create an electric field that either assists or opposes the gate field. Let's understand these four components. So first component is phi GC. Phi GC is basically phi F minus phi F when you have a metal gate. Okay, when you have a polysilicon gate, at the time you have a phi GC equal to phi F of substrate and phi F of gate. Both sides you need to find out the Fermi potential. However, for metal gate you need to find out the work function of the metal. Second component is minus 2 phi F because you wanted to invert the surface potential. So if let's say the bulk potential is phi F, you want phi S also to be phi F. Okay, that means total change in the potential is phi F to minus phi F, meaning minus 2 phi F. What is the charge density in the depletion region? So we already know that the charge density in the depletion region is given as minus 2q under root 2q Na epsilon Si. In bracket you have phi S minus phi F. So at inversion, phi S becomes phi F, so this becomes minus 2 phi F. Now one more phenomena I wanted to introduce over here is when you have a body which is not grounded, body at some different potential, what happens is out of these four terms, the third terms affect the most. Okay, because phi GC is the material property, does not get changed by the VSB. The second component also does not change by VSB a much. The third component changes a lot with respect to VSB. So the depletion region charge density becomes minus under root 2q epsilon Si Na minus 2 phi F plus VSB. We already know from the junction physics, PN junction physics, that when you apply the voltage, it get added over here. Okay, so what is the equivalent voltage component added into the threshold voltage because of this charge density? So the voltage component would be minus QB divided by Cox. Now the fixed positive charge density Qox is also there in the oxide. What is that? So when you make the oxide layers, sometimes because of the defects, there are some positive charges exist in the oxide. Because of these positive charges, there is a built-in potential. What is that potential is? That potential is Qox divided by Cox. What is the total threshold voltage of a MOSFET when there is no bias? Phi GC 2 phi F QB naught divided by Cox, Qox divided by Cox. We could have taken all the signs positive also, but at the time you need to keep all the values of these terms you need to put in a magnitude, not with a sign. But when you are taking this as a plus, this minus, this minus, this minus, you need to, whenever you are calculating, you are solving any numerical, you need to take all the quantities with the sign. For example, phi f is always negative for n MOSFET. Phi QB naught is also negative for n MOSFET, because in p-type semiconductor the charges are acceptor ions which are negative. Now let's understand, for non-zero substrate bias what would be the formula for threshold voltage. So we know that, so in threshold voltage only the third term will get changed from QB naught to, you will be having QB. Now mainly the third terms get affected, we already know this. So if you add and subtract QB naught and QB naught divided by Cox in this equation, what is going to happen is Vt becomes Vt naught minus QB naught divided by Cox. If you separately solve this QB minus QB naught divided by Cox, you will get minus 2Q Na epsilon Si divided by Cox. In the bracket you will be having minus 2 phi f plus VSB minus 2 phi f. So finally you can write the threshold voltage with respect to the substrate body bias. It's a Vt naught without the substrate body bias plus gamma, which is a substrate bias coefficient. The value of that is gamma equal to 2q Na epsilon Si divided by Cox, and multiplication with gamma, multiplication with under root minus 2 phi f plus VSB minus under root 2 phi f, where gamma is the substrate body coefficient. Gamma is always positive in case of a n MOSFET, and VSB is also positive in case of a n MOSFET. So this was all about today's lecture. Thank you.